Hello, everyone. I'm going to talk about xJsnark, a framework for efficient verifiable computation. This is joint work with my advisors, Babis and Elaine. So we have the same setting of verifiable computation in this talk, where where a client outsources the computation to some untrusted party, and this untrusted party is supposed to evaluate or run the computation along with some secret input, return the results back along with the proof to the verifier. And thankfully, during the past decade, there have been orders of magnitude in all aspects of performance. And we have now efficient constructions and implementations for what's called xJsnarks, which also which enabled us to get very short proofs and minimal verification times under certain assumptions. And this enabled a lot of practical applications spanning different areas, including cryptocurrency, certificate verification, and graph algorithms, and also image authentication. And in this talk, we're going to focus on one part of this, is the QAB-based pre-processing xJsnarks, which is the one that was used for many of the practical applications. Basically, basically we're going to focus on its front end. Basically, how we can use such construction. So typically, the computation to be verified is being expressed in a high-level program, and then it gets compiled to some kind of an arithmetic circuit or a set of quadratic constraints over a finite field. And this step has to be done carefully because the prover's time depends in a quasi-linear manner on the number of constraints or multiplication gates in the circuit. And what makes this problem interesting is that this has a different cost model than what we are used to in typical programs. So for example, bitwise operations are very expensive, and in comparison, like multiplication of circuit unknowns is much more expensive compared to multiplication by constants, for example. And currently, there are two ways where we can express computations as circuits. One way is high-level compilers, which can be categorized into classes. One class is the program-specific compilers. In this program-specific compilers, there is a different circuit generated by every program. And there have been a lot of interesting works in this area, like every compiler was providing different optimizations. There's also the concept of the universal circuit generators, which provides very interesting properties in terms of the expressiveness and the capabilities of runtime code generation, but it has less efficiency compared to the program-specific compilers. The other one is the low-level libraries or the manual libraries, which the programmer has to construct the gadgets manually and write the constraints manually. And these low-level libraries are preferred when we write performance-critical applications. And basically, to choose between both of these kinds is basically trade-off between the programmer's effort and performance. For many of the performance-critical applications, the low-level libraries were actually used. Okay, so the goals of xJsnark is that can we minimize the programmer's effort and in the same time get more efficient circuits? Basically, in the designer space, we would like to be in this shape. We would like to improve the circuit size and in the same time make the programming high level or easier for the programmer so that we can make writing applications faster and more easier. And also, can we develop more efficient circuits for frequent operations? Mainly, we would like to focus on cryptographic applications because almost all the applications that I've shown in the first slide have a cryptographic component in the circuit, because what makes xJsnarks attractive for many applications, I believe, is the zero-knowledge aspect, which means that there will be some zero-knowledge or some cryptographic gadgets in the circuit, like verifying hashes or signatures or encryption. So we would like to focus specifically on making techniques or development for these applications easier. And also, we are not limited to that. We're going to provide optimizations for random memory access applications, as we're going to see. Here in the figure, I just, actually in our benchmarks, we're going to show that our tool can get to the manual implementation, or for example, for SHA-256 and RSA, we're actually can achieve the efficiency of low level, but in general, we can't make a statement like this. Or like we can't say that it's always the manual level tool or like the low level tools are going always to be better. So a closer look at our motivation. So the previous high-level compilers provide very useful features and optimizations. However, I believe that there are few things missing before making these used widely. So the first is that the size of the circuit output is often larger than the manually developed circuits. Additionally, it requires extensive programming background or like knowledge of how the underlying xJsnark's circuit works. So the programmer is still responsible for many decisions. For example, choosing which, what is the efficient memory representation based on the memory workload. Also, the programmer is responsible for tracking bit width, avoiding overflows, and also adding casting statements in non-trivial locations. And for some applications, as we're going to show next, using high-level compilers, this actually is going to require more effort and background as low-level tools. And this application that I'm going to show actually appeared in 2 papers. Like one of them is totally independent. So these applications are not just side cases. So let's say we would like to do some finite field operations in non-native field, and a field that is different from the field where the xJsnark circuit operates. So let's say we have 2 elliptic curve points over a different field, and we would like to apply the addition formula of in affine coordinates, assuming all the error checks have been made. So in order to do this currently using high-level compilers or manual level tools, the programmer will have to do the following. Since this field is large, the programmer will have to divide every element into multiple chunks. Choosing the bit width of every chunk here is, like as we show in the paper, is not trivial. Like it matters in the efficiency and of course the security. And the programmer will have to implement subtraction manually. This typically involves adding some auxiliary constants, choosing very carefully. And then there will be a division operation done manually as well. This requires knowledge of non-determinism in order to write this securely. And also there will be multiplication later, which is going to increase the bit width of these elements. And the programmer will be responsible for choosing when to reduce or like to do mod operations to reduce the length of these elements. So as we see here, this is a very complicated circuit. There are many decisions by the programmer, and the complexity is going to be visible in both low-level and high-level implementations. So to give you like what xJsnark tries to do is to introduce parameterized native types and automates all of these decisions while even having more efficient circuits than before. So basically in our code, to show the code that for adding the points, in our framework, the programmer is going to write code like this. It's like the actual equations. And I have to emphasize here that this is not hard-coded for a certain field. Actually, the programmer can define whatever field he'd like the circuit to operate on. And then during the editing, in the framework, the programmer can choose which field he'd like the variables to be in. And here, as you see, the programmer can define long fields, short fields, or even work on the native. And the backend adapts its implementation according to the circuit structure and according to the fields that the programmer is working on. Okay, so the outline of xJsnark, the programmer writes the code in our xJsnark extension, which is developed as a Java extension on top of the JetBrains MBS framework. And it gets type checked in the front end, and it gets transformed to a Java code that generates the circuit. And then in the back end, before we do or generate any constraints, we do initially a complete analysis phase of the circuit to study how every variables are being used, what are the parameters and so on. And then in the second phase, we generate the circuit. And then after we generate the circuit, we even apply more optimizations. One key point here is that we implemented all the steps from the high-level code to the circuit generation in order to be able to keep track of the programmer's intention and be able to make better decisions. Under the hood, we have, for the back end, we implemented optimizations for both short and long integer operations. Also, we have a new optimization for read-only static memory, which helps for techniques like the S-box, which appears in the ES, and also pre-computed computations, which could appear in floating point operations when we store, because it's expensive sometimes to do many operations in the circuit, so we can pre-compute them and store them in read-only memories. And also we do automated identification of the efficient memory representation. And also we do, in order to reduce the number of multiplication gates or constraints even further, we apply multivariate polynomial minimization. We have implemented a version that's customized for the QEB-based xJsnarks. In terms of the front end, it's currently, as I said, developed as a Java extension using the JetBrains MBS framework. It provides parameterized types for long integer and short integer and for field operations as well. It hides the complexity of the back-end implementation and enables better use of non-determinism, which is basically how to set the values of external witnesses in the same environment. And we also have custom IDE support, so we give optimization hints interactively that are customized to the snarks, and we have error checking for the new type system. One limitation for this, though, is that it requires development to be done in this framework, which would require the users in the beginning to get familiar with the environment. Okay, so I'm going to select just a couple of points of these for the sake of time to talk about. One point is the random memory access, like what we do to improve. So basically for the read-only static memory, which given an element of hard-coded values and unknown index R during runtime, return the value at a specific index. So basically, the currently available ways to do it are either Merkle trees or to do a linear scan or to use a permutation network. And in the paper, we describe a new optimization that is specific to the cost model of the QEB-based xJsnarks. Mainly, it relies on the multiplication by constants are cheap, and also it relies on non-determinism. And it's based on dividing or partitioning this array into square root of n partitions, where we construct a linear system offline for every partition, and then in the circuit, we just check a membership by checking whether the solution provided by the prover belongs to one of these square root of n linear systems. In comparison with earlier work, this scheme is, as you see, it doesn't look from this table that it's more efficient. Actually, asymptotically speaking, the Merkle tree is more efficient. But as we're going to see when we speak concretely or evaluate or get the actual value for constants, it's actually better than all of these schemes when the size of the memory is small and for any memory access or for any number of accesses. So for example, it's better than in the very first part, it's better than the nearest one, it's better than the linear scan, and later it's better than the optimized permutation network. And I have to say the current compilers don't use the optimized permutation network, but we just include it here for fairness of comparison. Also, we use what we call a smart memory structure. So basically, based on the workload of the program, we identify which memory algorithm to use to represent the memory accesses in. So basically, we have 3 possible memory algorithms, including the linear scan, the routing networks, and our read-only memory technique. And we decide what's best based on the program, analyzing the program. And I have to say that we don't group all the memory accesses into just one memory. We have to study every memory separately. And this gives us a more efficient representation for object-oriented programs. So xJsnark provides the ability to write, the programmers to write different class definitions. And the programmer can call methods on references that are unknown during runtime. In order to implement this efficiently, we found that every class definition has to have a smart memory structure for each of its attributes. Also, as another feature, we have what we call external code blocks, which actually enables the programmer to make use of the non-deterministic properties of the xJsnarks. So basically, let's say if we'd like to write a sorting code, we don't need anymore to write merge sort code as in the previous work. We actually can define the code this way. The programmer can say that the sorted array is going to be a witness, and then we have an external code block that is going to be completely executed outside the circuit. In this case, for example, the programmer can call any Java library to sort and then figure out how the elements are going to be mapped. And then in the circuit itself, we're going to verify the permutation that the inputs and the outputs are similar, and we just verify the sorting condition. Okay? This is actually going to result into more efficient circuits than before, and I have to say that this verified permutation is actually a high-level opcode or an instruction in our program so that the programmer doesn't have to get into writing switches or setting witnesses and so on. Okay, so in terms of evaluation, we evaluated into multiple contexts. So in comparison or for cryptographic primitives, we compare with other compilers for SHA-256 and RSA and ES. For all of them, we show that our circuits are more concise, and in some cases as well that it does not require high programming effort. And for this table, for the SHA-256 and the RSA, our implementation actually match the manual implementation. For this version, though, the ES does not, but for our most recent version of the code that we posted, we matched the manual implementation for ES as well. And to give you also a sense of why these things are useful, here we compare what would be the proof time and the proving key size and the memory usage when we apply our optimization. So for example, for the EES, when we apply it for a 300 block circuit, we see here optimizations on all of the different aspects, including the proof time, the proving key size, and the memory usage. Also for the random memory access applications, we show here, okay, so we have two options, either to write, just for fairness of comparison, to write merge sort code on our xJsnark, and in this case, we also perform better than previous work. This is due to the adaptive memory techniques that we have and other low-level optimizations. And if the programmer chooses to use the permutation verifier to get better numbers, or like to write the sorting as in the example that I showed, it actually gets orders of magnitude better. Additionally, we've chosen one of the applications that were developed manually, and we wrote it using our application, or our xJsnark. And here we show that our framework was able to get to the manual implementation of the zero cache. I'm not going to say it beats the manual implementation because it's always possible to modify any manual implementation to be better, but at least we can now take manual, automated tools to reach manually developed tools for some applications. Okay, so in terms of the limitations and the future work, we plan to integrate other optimizations. Till this point, we are also considering other applications and including more optimizations. We plan to integrate with other front ends. We would like to customize the optimizations for other xJsnark constructions. We've seen in this conference multiple other backends, so we would like as well to make our optimizations compatible. And we would like also to do automated testing for missing or incorrect constraints, because it's easy, or it's relatively easy to check the correctness of the circuit, but how can we make sure that any of the constraints have not been, we need to make sure that all the constraints have been written correctly. So we have made a partial release of xJsnark on GitHub, and more improvements and refinements are going to be posted, and we posted the manually developed optimized circuit or gadgets as well in our manually developed library. With that, I'm going to conclude my talk. Thank you, and please let me know if you have questions.
Hi. Thank you for your talk.
Thanks.
Also, thank you for referring to our work as QAP-based, not linear PCP-based. So my question is, there have been all kinds of gadgets that optimize the representation of different subcircuits as quadratic arithmetic programs. Is it easy to integrate in your framework new potential gadgets that people might be coming up with?
Okay, so let's say if my xJsnark does not implement a certain gadget in the most efficient way, we provide the programmer can actually develop or do the manual development in the framework itself. So we basically provide the programmer to be able to define these external witnesses, which actually looks like the manually developed or manual development exactly. So the programmer would still be able to integrate these gadgets. Or you're asking about, okay, so if the question is about if there is a hard-coded gadget that we would like to integrate directly in our framework, we currently don't support this, but it's possible in the future that we can do it.
Okay, thanks.
Let's thank Ahmed again.
Okay, thank you.